Okay, everyone, let's go ahead and start. I have my cursor. Okay. All right, guys. So yeah, I'm going to tell you a little bit about DataJoint. My name is Kushal. I work at DataJoint as a neuroscience data engineer, and I've been with the company for it's about 11 months, almost a year. And before that, I was completing my PhD in neuroscience at Texas A&M University. So we'll talk about integrating DataJoint pipelines and NWB. And I'm going to open it up to you guys. If you guys have any questions at any point during the presentation, just put your hand up, and yeah, we can keep this pretty informal. There's not a lot of people here, so. Uh, so if you haven't heard of DataJoint, we'll start there. DataJoint is an open source library for defining a data pipeline to organize scientific data in a relational database with automated computations. That's a lot of words. So more simply put, DataJoint interacts with a MySQL database on the back end to efficiently perform data processing and analysis through programming languages that y'all are probably familiar with, like MATLAB and Python. DataJoint was founded in DataJoint began in the lab of Andreas Tilias in 2009. It was developed for MATLAB, and now we've been increasing support for Python to the point where I think we have slightly more developments in Python than in MATLAB, but we do still support both. So I imagine most people in this room are probably more comfortable with Python anyway. But at the end of the day, DataJoint's goal is to try to automate your day-to-day mundane pipeline operations that start from ingesting metadata about any of your acquisitions to processing and analysis, and also allowing for distributed access and computation. So it scales really well for collaborations. Now, we've used DataJoint to create standard pipelines for neuroscience experiments with the goal that we want to get from, regardless of the techniques that you're using, we want to get from your raw acquired data to your processed results as painlessly as possible. And we're thinking not just on one machine, but rather on a larger scale of an entire lab, or even a larger collaboration across institutions, with data integrity and transparency at the forefront throughout the pipeline. But why, right? And I think everyone in this room has an idea of why, but if we go all the way back to the beginning, neuroscience studies are extremely complex. They always have been, but they are getting increasingly complex, and successfully executing these studies is starting to require needing to overcome a lot of technical and organizational challenges. Collaborations are also becoming increasingly common, and standardization is becoming essential. I could go on for hours about how terrible it was for me to collaborate across institutions during my PhD because we didn't use technologies like this. But I'll maybe come see me if you want to hear about that. But ideally, when we're collaborating, what we would like to see is we have our sort of metadata, our subject information, our pipeline information in our heads, and ideally what we want to be able to do is just seamlessly stream that into the head of our collaborators, right? And unfortunately, that's not how it works in practice. So what you end up with is kind of this mess of files, and your notes might be your notes may not even be electronic. Furthermore, if your collaborators are using a different OS than you, that creates all kinds of problems. If you give them your scripts, they don't run from Windows to Mac and all of this. So it creates a lot of issues, which are compounded by organizational challenges, right? There's a lot of things that scientists have to keep track of and manage just in organizing data and data systems for themselves. So there's all kinds of questions. For example, how do you do analyses over many recordings, or what happens if you find a mistake in your processing chain, or what happens if you're collaborating with someone and you find a mistake in their processing chain? How do you go back, correct your issues, and how do you version track all of these things? So to summarize, if you're using conventional approaches to data management, chances are that all of this is required from the scientist, where you have to manually, depending on the task that you're trying to do, you have to manually perform a task. For example, to select sessions based on a criteria, you have to comb through directories manually. If you want to update to a new analysis method, you have to manually note where your old results are kept and how your new results are going to be tracked, amongst other things, as you can see. And sharing data also becomes very difficult if you're just using something like maybe zip files or external drives and things like that. So this is where the need for standardization really becomes apparent, as if it wasn't already. And DataJoint pipelines are working to help standardize the data management and analysis. So what these pipelines are doing are they take the collection of all the different things in your experiment, right? That could be anything from your animal all the way down to your data, and basically put them into a hierarchy. So each node here represents a table that's declared in the database, and the order of the tables is how the pipeline will expect to receive data. So the tables at the top expect to receive data before the tables at the bottom. Now you might notice there's a color and a shape scheme going on here, and that is important as well. So the green rectangular tables are manual data entry tables, so they expect the scientist to enter those tables. Basically, the scientist is responsible for entering data into those data tables. So you would enter in information, for example, about your subject or your session, or if you're working with EFIS, you enter information about your probe. But then you get to your first oval purple colored table, and what that table is doing is it's a computed table. So what it will do is, based on the information that you enter in the manual entry tables, it will go ahead and automatically run a script that we've pre-written to extract the metadata, for example, about your EFIS file, and insert all of that information into the table. So you are not sitting there having to type that up. You just call one line of code. You call EFIS recording.populate, and it will populate that table in the database. So it will do all of the it will parse the metadata, and then it will insert it into the SQL database. So you don't need to know any SQL for this. You can work through it with Python. And then it will propagate that to the next computed table, which is the LFP. So it will basically store all of the LFPs that it extracts from your EFIS files, which you can point the pipeline to where your EFIS files are stored in one of those green tables. And then it will just carry out the computation for extracting the LFPs. It will carry out similar processes for triggering kilosort. Once you've defined a set of parameters, let me see if I can get my cursor over there. There we go. Once you've defined a set of parameters in this table and given it a clustering task to say use kilosort 3.0 or use kilosort 2.5 or whatever it is that you use. And it will trigger kilosort, but not only will it do that, but it will parse through the outputs of kilosort, or it can parse through the outputs of any curation that you've done, and it will put all of that information back into the database. So this pipeline is created to basically make it really easy for you to know where your data is, and then if you have a collaborator and they want to know how you're querying your data or where it's stored, it's kind of you can send them a Jupyter notebook saying, hey, this is what I use, and it's going to be the same as long as they have access to the database. So as long as they have credentials set up, everything else remains the same. So you might be able to see some of the standardizations that are coming into play here, but there are some additional standardizations, or at least good best practice methodologies that are not immediately apparent, which I'll talk about in the next slide. So let's say you have an animal, you have 3 animals in your database, and obviously you would expect to have a lot more in practice. And say two of the animals have 2 sessions each. These could be any sessions, could be EFIS, imaging, behavior, fiber photometry, etc. But for whatever reason, let's say animal number 2 doesn't make it to the end of your experiment, and you want to remove it from this animal table. Typically, you would have to go through and delete all of the sessions downstream yourself, or you just end up deleting the animal. And I did this many times where I ended up deleting something from my notes, and then I never caught up to the data that was in the computer, and so I ended up with orphan data. So if you do this in DataJoint where you delete animal 2, it will automatically delete anything downstream that references animal 2. So any analysis, any sessions that were generated for animal 2 are deleted automatically. So this cascading delete ensures that there is no orphan data left, so you're never looking back saying, hey, I don't know where this data goes. Another really convenient feature is automated computations. So say you want to compare two different versions of Keylosort, or you're considering maybe taking up Keylosort 4, which we'll have support for pretty soon. It's on our roadmap. So if you want to see what that would look like on your data set, basically as long as you define it in the parameter table that you'd like to use Keylosort version 2.5, and you give it all the relevant parameters, it's just one line of code to trigger the computations for if you want to compare the two. It will go ahead and do that step automatically and give you the clusters that keep track of the version, the animal, and the session. So you can basically trace your way back and find which analyses were done on which of your animals across which of your sessions. So going back to the collaborative aspect of this, DataJoint Pipelines really help standardize the process of just about every task that you might want to do within your lab or with your collaborators, where if you need to select based on a session or based on a particular version of Suite 2P, for example, that would be essentially one command. There's the cascading deletions that we talked about. So if you have new analyses and you choose to delete your old data, you can delete at the session level, and you don't have to worry about any data left downstream. Distributed computations are automatic, and the relationships are maintained pretty naturally because of the way the pipelines work. At this point, I want to talk about DataJoint pipelines and how they incorporate NWB export into them. So if it hasn't been really clear until now, maybe this will help make more clear that DataJoint sort of operates on a level above, don't mean to say above, but before perhaps you're converting your data to NWB files and uploading to Dandy, because basically you have your data acquisition, and then you pre-process your data, and then that pre-processed data can be converted into an NWB file. So you can see there's a lot of shared goals here in terms of standardizing the processing, standardizing how other people are able to access your data. You also have other things that DataJoint is capable of doing, like user-defined processing. Like if you're doing spike-triggered averaging or something, DataJoint you can add a table for that in your pipeline and package that into your NWB files as well if you want. Here's just a little more illustrative diagram that shows how each individual table in the DataJoint database can line up to different NWB objects. So this is a little bit more explicit and gives you a better idea of how each of the tables lines up to different objects within the file. But let's get into NWB, DataJoint and NWB interoperability approaches. So basically how you can take your data from DataJoint and put it into NWB, or take your data from NWB and put it into DataJoint. So we'll start with, we'll talk about three different modes of interoperability, and these are ordered by complexity. So number one is the easiest, and number three is arguably the most difficult. Each has its advantages and disadvantages, so we'll start with number one, which is just an export from the pipeline. So say you've processed your data through the pipeline, and now you're getting ready to publish and share your data after you've done all of your analyses. And this makes use, again, of an existing pipeline, but it is unidirectional. So DataJoint processes all of the data, and then you convert to NWB, you upload to Dandy, but you can't really go backwards with this approach. So that's a downside to it, but it's a very straightforward, very easy to implement version. So we do currently support this within the pipeline itself, and I'll show you where the pipeline lives. So if you guys want to check this out, you can. It's all open source. But this is basically, I would say, 95% of the code that you need to really write out, or rather that we've written out to make the upload. All you would need to customize are your session keys and define a few other variables here to have this upload go through. And obviously you'd need your Dandy site ID and APIs. defined. But it's basically, it's still minimizing a lot of the work that you have to do. And actually, so as I mentioned, this is for EFAS data and NeuroPixels electrophysiology. What I'm going to be working on is the export for calcium imaging data actually at this workshop. So presumably by the end of this weekend, we'll also have support for packaging calcium imaging data to NWB files and uploading to Dandy Archive. So the second interoperability mode is actually not one that we support as DataJoint, but because DataJoint is open source, we have had people fork our repository and adapt it and adapt the pipeline and make it their own. So this example actually comes from Lauren Frank's lab at UCSF, and they have a their data management pipeline is called Spyglass. Maybe some of you have heard of it here. But what they do is they take advantage of the fact that DataJoint has two types of data that it can store within the pipeline. One of those are the internal data types that are basically what you saw in the figure that I showed, the pipeline diagram that I showed you earlier. But there's also these external data types that can store entire files within the pipeline. And so that's what this does, but it does keep the file separate from the rest of the pipeline. And as I mentioned, each of these has an advantage and a disadvantage. So while this approach is not very difficult to implement, again, it's easy to implement and manage. All of the metadata lives in one file. It's queryable just like the rest of your data would be with DataJoint. The disadvantages are that it can get you could get to some very large physical files because you're storing the NWB files right there, and it's difficult to grow this as new data is added to it. So to get around this, there is a third approach, and this is arguably the most complicated to implement, but it's basically a one-time cost, and once it's coded properly, this would be a pretty good way to use NWB files and DataJoint pipelines as one, and that's by using something called the DataJoint attribute adapter. And I won't get into this for the sake of time and complexity, but if you are interested, feel free to reach out to us. I'll put up our support in our Slack channels, so you can always email us or reach out if this is something that you're interested in, and we'll put you in touch with Dimitri, our founder, who will have extensive knowledge about this, and he'll also be here tomorrow, so if you want to talk directly to him, you can feel free to do that. So yeah, the advantages here is that it allows for flexible query and fetch on the NWB objects themselves. So basically you get the advantages of DataJoint querying, which is very quick and very fast, and it can adapt really quickly to new data. You have the managed cascade deletions that I mentioned, and the NWB files stay outside the pipeline. So this can scale much more easily. The disadvantages, as I mentioned, is the implementation primarily, and there can be multiple files per session. Yeah.
Can you quickly explain the difference between the attribute adapter
Yeah. Yeah, between this and this. Yeah, so this is actually storing the NWB file itself within the pipeline, whereas the other approach is taking the NWB objects that are within the NWB files, and they are actually they are stored as basically a column in the database. So it's basically extracting rather than just storing the NWB file as the NWB file structure, it's actually taking out the information and actually putting it into the pipeline. That's essentially how it can be thought of.
So you still have the NWB file inside, but you're referencing a particular object.
Yes. I think that's the best way to, yeah. So if you would like to check out tutorials and documentation, that is found, we have tutorials on our GitHub for NeuroPixels, for calcium imaging. We are in a little bit of a little bit of a flux with the tutorial, so we are updating them. So right now, they show you how to set up a DataJoint pipeline for neuropixels electrophysiology or calcium imaging. But right now, if you want to know specifically about how to package your data to NWB using DataJoint, please reach out to us, and we will get you what you need. They're just not available on GitHub yet. They are coming in probably a few months, but and then the documentation lives at datajoint.com/docs. So you can look into that yourself if you want, but if you don't want to do any of that, you can do this instead. And I will say primarily the support at datajoint.com, the email is probably the best way to reach us. Those emails come to me. So I will forward them to the relevant individuals who will be able to help you based on your question. So that's probably the best way to reach out, but we are really active on pretty much all of the other ones as well. So office hours, we do by request once a month. GitHub issues, if you're a more advanced user and you feel comfortable starting an issue, please don't hesitate to do so. We monitor Stack Overflow for the DataJoint tag, so if you have any questions, you can ask them there. We have a Slack if you'd like to join that, and we do respond there fairly quickly. And Dimitri himself is very active on there, so he's our founder, and so he can answer just about any question that you could have about adapting DataJoint for your implementation. And we do have a chat feature on the website as well, but you're probably better off using the support here. And finally, I just want to acknowledge in particular the NIH U24 grant that makes creating and maintaining these open source pipelines, as well as DataJoint open source as well, just maintaining all of that possible, as well as our U24 scientific steering group, the proposal contributors, and the DataJoint team. Yeah, I think that's pretty much all I have for you, and I think I'm just a couple minutes if anyone has any questions. Go for it.
Sorry if this question's a little bit basic, but I'm curious, like, in the actual SQL world, if I had multiple experiments, would they just save a separate schema, and within each schema there'd be specific tables, as you kind of like mentioned before, or like how does that work in like actual SQL land?
In actual, so yes, it depends on how you choose to organize your data. You can, so we do declare multiple schemas. So basically these are actually what you're seeing. Let's go back to the pipeline diagram. Okay, so what you're seeing here is actually, yeah, these are different databases within the MySQL server, and each database contains, so these schemas all contain, tables that are thematically related, essentially, right? So the subject, so here we just show the one subject table, but the subject schema actually contains tables for things like surgery and injection, and all of those are also present. But basically we enforce primary key relationships. So basically there's a primary key in the session table to the subject table, and that's how it works in the SQL land. Mm-hmm. Good question. All right, thanks guys.